A bridge doesn't collapse in a single moment. The real story begins long before the crack appears. Engineers study something called strength of materials, the science that tells us how materials behave when forces try to break them. When forces act on a material, internal resistance develops inside it. This internal resistance is called stress. The greater the applied force, the higher the stress inside the material. The first and most common type is tensile stress, when forces pull a material apart. Bridge cables experience tensile stress every second as they hold the weight of traffic. The opposite is compressive stress, when forces push and squeeze the material. Columns in buildings constantly resist compressive stress from the entire structure above. Then comes shear stress, where forces try to slide one layer of material over another. Bolts, rivets, and joints must resist massive shear forces. And finally, bending stress, a combination of tension and compression inside beams. The top compresses, the bottom stretches. To understand material strength, engineers run laboratory tests. In a tensile test, a sample is pulled until it finally breaks. This test reveals critical points like yield strength and ultimate strength. When stress exceeds the material's strength, failure begins. Concrete typically fails under compression. Steel usually fails under extreme tension. On real projects, engineers calculate stresses before construction begins. Modern software maps stress inside structures to prevent disasters. When stresses exceed the strength of materials, structures fail. That's why inspection and testing are critical. Engineers also use non-destructive testing, like ultrasonic inspection, to detect hidden flaws. Regular monitoring ensures stress never reaches dangerous levels. Every skyscraper, bridge, and dam survives because engineers understand stresses. Behind every safe structure is the science of strength. But not all materials fail the same way. Some are ductile, stretching before they break. Others are brittle, shattering instantly without warning. This difference is a matter of life and death. Ductile materials like steel provide safety by giving engineers a visual warning before total collapse. Then there is the hidden enemy, fatigue. It's when a material fails under repeated loads. Like a paperclip bent back and forth, materials grow tired and eventually snap. Airplane wings and engine parts are designed to resist millions of these stress cycles. In the past, ignoring fatigue led to some of history's most catastrophic engineering disasters. Even temperature can be a source of stress. Materials expand and contract as they heat and cool. Engineers install expansion joints to allow structures to breathe without cracking. Without these gaps, thermal expansion can generate enough force to buckle heavy steel rails. Under high heat and constant load, materials undergo creep, a slow, permanent deformation over time. In jet engines, turbine blades must resist creep at temperatures hot enough to melt ordinary steel. Every material has an elastic limit. Stay within it, and the material returns to its original shape. Cross that limit, and you enter the plastic region, where the damage becomes permanent. This linear relationship is Hooke's law, the cornerstone of predictable engineering. Today, we are building with composites, materials designed at the molecular level for extreme strength. Carbon fiber is 5 times stronger than steel, but light enough to lift with one hand. These materials are revolutionizing aerospace, allowing for lighter, more fuel-efficient aircraft. To ensure absolute safety, engineers always use a factor of safety. An elevator is designed to hold several times its maximum capacity, just in case. Using finite element analysis, we can predict exactly where a structure will fail before it's even built. We can test thousands of design variations in a virtual wind tunnel or earthquake simulation. History is our greatest teacher. Every collapse provides data that makes the next bridge safer. Sometimes it's not just the weight, it's the wind and resonance that tears a structure apart. Modern skyscrapers use massive dampers to counteract these dynamic forces and keep the structure stable. Wind tunnel testing is now a standard part of high-rise design to manage vortex shedding. Corrosion is the silent killer of infrastructure, eating away at the material's cross-sectional area. As the area decreases, the stress levels skyrocket, even if the load remains the same. Constant maintenance is a heroic effort to keep the science of materials on our side. The future is smart materials. Concrete that can heal its own cracks using embedded bacteria, and alloys that remember their shape, ready to reset after an earthquake. Take a marvel like the Golden Gate. It's a testament to the mastery of tension and compression. Each main cable contains over 27,000 individual wires, sharing the burden of stress. The foundations deep below the water must resist massive compressive and hydrostatic forces. In many ways, a bridge is a living thing, constantly adjusting to the forces of the world. Understanding materials is more than just math. It's a massive ethical responsibility. Millions of lives depend on the invisible calculations performed by engineers every day. The field is always evolving, with new discoveries making the world safer, one material at a time. Every failure is a puzzle, waiting to be solved by the engineering detective. Soon, we will build on other worlds, pushing the science of materials to its ultimate limit. Tension, compression, shear, and bending. These are the forces that shape our reality, because when we master materials, there is no limit to what we can build. Strength isn't just about power. It's about the precision of science. Thanks for diving into the mechanics of our world. Keep building, keep learning. Follow us for more deep dives into the engineering that holds our world together. Thanks for watching Concrete Hustle. Stay safe and keep building.